This conference will now be recorded.
So good morning, students, and today's class will continue with where we left off last time. So last class we were discussing about the various shifts, the different types of chromophores and their effects on the absorption spectrum. Today we'll see one more factor which actually causes some changes in the spectrum. When we say changes in spectrum, it always relates to either the position of the peak or it relates to the height of the peak or the shape of the peak. These are the effects that we see in spectra. So today we are going to discuss about the effect of solvent on spectra. UV visible spectra. So solvents must be transparent in the region to be observed. This is the primary requirement for a solvent. Solvent must be transparent in the region to be observed. That means you are going to be doing your experiment at a particular wavelength. At that wavelength, the solvent must not show any absorption. It should be transparent. If we say that the solvent is transparent, that means that it will not absorb that wavelength of radiation. The wavelength where a solvent is no longer transparent is referred to as the cutoff. So if we say for a given solvent, the cutoff is 210 nanometers, then 210 nanometers and below, the solvent will be absorbing radiation. At wavelengths 210 nanometers and below, it will absorb. But above 210 nanometers, it will be transparent. So the wavelength where a solvent is no longer transparent, in the example I gave, say 210, is referred to as the cutoff wavelength for that solvent. Since spectra are only obtained up to 200 nanometers, solvents typically only need to lack conjugated p systems or carbonyls. That means unsaturation should not be there, because as we have seen a few classes earlier, it is in the UV visible region, it is only the pi electrons and the n electrons which contribute towards spectra, because only they can be excited by the energy possessed in the UV visible radiation. So we are referring to radiation above 200 nanometer. So very close to the extreme end of UV. Usually if we say 180 to 380 is UV range and 380 to 780 is visible range. But if you go below 200 nanometer, you see lot of disturbance, lot of noise will be there. And that is why measurements are usually done from 200 nanometers. So if we are working at 200 nanometers and a longer wavelength, then what we see is that these solvents which we use to make the solution must not absorb uh, at those wavelengths. So they will not absorb if pi electrons are not there, or you don't have n electrons in the molecule, then it will not absorb. The common solvents and cutoff wavelengths have been listed in this table. You have the solvent acetonitrile, you have whose cutoff wavelength is 190 nanometers. You have water, cutoff wavelength being 190. What it means, water, say for example, it's a very commonly used solvent. So we say the cutoff wavelength is 190 nanometer. That means above 190 nanometer, water will not absorb UV visible radiation. So it can be very easily used as a solvent for observing UV visible spectra. Similarly, acetonitrile can be used very easily above 190 nanometers. It will show no absorption in that region. Then you have cyclohexane 195, isooctane 195, N-hexane 201, methanol 205. That means if you want to observe at 200 nanometers, methanol would not be suitable because it will also show absorption at 200. Above 205, it will not show any absorption. 95% ethanol, also 205. 1,4-dioxane 250, chloroform 240. I particularly mention chloroform because for many of the organic compounds, chloroform is a very good solvent. It will dissolve the compound. But if the wavelength of absorption of the organic compound is shorter than 240 nanometer, then chloroform is not a suitable solvent for spectroscopy because chloroform itself will absorb till 240 nanometers. So in that case, we can choose ethanol. So considering all this, ethanol is considered a very good solvent because it dissolves both organic and inorganic compounds and polar and non-polar compounds, and its cutoff wavelength is also quite short at 205 nanometers. Water may not be able to dissolve many of the organic compounds, otherwise water is also considered a good solvent. Every solvent has a UV visible absorbance cutoff wavelength. The solvent cutoff is the wavelength below which the solvent itself absorbs all of the light. So below the cutoff wavelength, that is shorter than the cutoff wavelength, the solvent itself absorbs most of the light. I have mentioned all of the light because solvent molecules are present in very high concentration in your solution compared to your solute molecules, because in UV visible spectroscopy, we always use very dilute solutions. So dilute solutions means solute molecules are very few, solvent molecules are in excess, and that's why they absorb almost all the light. So when choosing a solvent, be aware of its absorbance cutoff and where the compound under investigation is thought to absorb. You have to consider two things. What is the solvent cutoff and what is the wavelength at which the compound absorbs? So you will choose your wavelength for your experiment based on this second part, that is compound under investigation where it absorbs. So based on that, you will choose the lambda or the wavelength for your measurements. Now you have to consider the solvent and its cutoff. If the cutoff is shorter than the wavelength to be used in our experiment, then it is okay as a solvent. If the cutoff wavelength is longer, is more than the wavelength we propose to use in our experiment, then the solvent is not suitable in this experiment. Even if they are close, it is better to choose a different solvent. So the cutoff should be very short compared to the wavelength that we are proposing to use in our experiment. Solvents must preserve the fine structure. This is the other feature that is very important while you're choosing solvents. So when we are choosing solvents, the first primary thing that we would do is we see whether the solvent can dissolve our sample. Second thing is regarding absorption. At the wavelength at which we are proposing to do our experiment, we should see that the solvent does not absorb. So we have to consider its cutoff. The third thing would be the solvent that we are using must preserve the fine structure wherever possible. What is this fine structure? I will show you a pic after this slide. This is mainly because of the vibrational and rotational transitions that are superimposed on electronic transitions. We have seen earlier that whenever you have an electronic transition, you also have a number of vibrational and rotational transitions. And these come as either rotational as lines, vibrational as narrow peaks. They're all superimposed on the broad electronic absorption peak. So if hydrogen bonding is seen in a molecule, it complicates the effect of the vibrational and rotational levels which are superimposed on electronic transitions, and you see a large band there instead of the fine structure due to the vibrational and rotational energy transitions. A non-polar solvent. Now, the solvents could be the non-polar or polar. A non-polar solvent does not hydrogen bond with the solute, and the spectrum of the solute closely approximates the spectrum that would be produced in the gaseous state. in which fine structure is often observed. Whenever you see in the gaseous state, say for example, benzene is a liquid, and if you convert it into the gaseous state and in the vapor form, if you take a spectrum, then you will see all the fine structure. That is, the individual vibrational and rotational energy transitions will give an effect in the form of small peaks, not a straight line. I will just show in the next slide. This is observed even in a solution that is made with a non-polar solvent. So benzene, if it is dissolved in a non-polar solvent, then also it will give a spectrum similar to what we get in the gaseous state, because the non-polar solvent does not hydrogen bond with the solute. So similarly, on the other hand, in a polar solvent, the hydrogen bonding forms a solute solvent complex, and the fine structure may disappear. Because of this hydrogen bonding, which forms a solute solvent complex, the fine structure may disappear. And the more polar the solvent, the more the disappearance of the fine structure. So dipole-dipole interactions are less in non-polar solvents. Hence, the more non-polar the solvent, the better. This is not always possible because the substance may not dissolve in the highly non-polar solvent. Then the whole exercise is a waste, because primary concern is the solvent should be capable of dissolving the compound concerned. If it is dissolving and you have a number of solvents which can dissolve, the most non-polar would be best, because it will show all the fine structure. Now, this is what I was referring to, spectrum of phenol in isooctane and ethanol. Isooctane being more polar, you will see, isooctane being more non-polar, you will see the uh, fine structure. This is what is the fine structure, the small peaks that are evident. But if you take a polar solvent like ethanol and dissolve phenol in it, then you will see just a peak like this, as indicated by the blue graph. So you will get a broad single peak. You don't get the fine structure. So the fine structure helps you to get a better idea about the structure of the molecule. So it depends upon what is your, if you are only going for quantitative and estimations, you can always do it in a polar solvent because you're not so interested in this fine structure. But if you're going for identification, then the fine structure would help you a lot. And that's when we would like to make our solution in a non-polar solvent. Choice of solvents. How do you make the choice? It should not itself, the solvent should not itself absorb radiations in the region under investigation. It should be less polar so that it has minimum interaction with the solute. So the most commonly used solvent is 95% ethanol, because as I told you, it dissolves most of the polar and the non-polar compounds. 95% ethanol is also cheap. It has, of course, a good dissolving power, and it does not absorb radiation above 210 nanometers. So all these are its plus points, because of which it is very commonly used as a solvent in UV visible spectroscopy. So the effects of solvents we will summarize now in the coming slides. The position, what is the effect of solvent on spectrum? The position and intensity of an absorption band may shift when the spectrum is recorded in different solvents. A dilute sample solution is always preferred for analysis. So the solvent is very important. It becomes the main absorbing entity if it is capable of absorbing that wavelength of radiation. So most commonly used solvent is 95% ethanol, as it is cheap, has good dissolving power, and is transparent down to 210 nanometers. The fine structure is better revealed in spectrum with non-polar solvent. Position as well as intensity of absorption maxima get shifted for a particular chromophore by changing the polarity of the solvent. That means the intensity of the peak and the position of the peak both will change by changing the polarity of the solvent. By increasing polarity of solvents, there is no effect in case of dienes and conjugated hydrocarbons. So for such type of compounds, you can use any of the solvents. The solvents will not show any effect on the spectrum. However, for alpha beta unsaturated carbonyl compounds, you can see shifts, and these shifts are of two different types. That's because alpha beta unsaturated carbonyl compounds will show two types of transitions, the N pi star transition and the pi star transition. Because of oxygen being present in the carbonyl compounds, it will have N electrons, and also because of unsaturation, you have pi electrons. So both N pi star and pi star transitions are possible. And these two transitions will undergo different types of shifts. So the N pi star transition, what type of shift it will undergo? Absorption band moves to shorter wavelength, that is blue shift, or it's also called hypsochromic shift, by increasing the polarity of the solvent. So absorption band, due to the N pi star transition, moves to shorter wavelength or undergoes a hypsochromic or blue shift by increasing the polarity of the solvent. Why this happens? This is because the ground state is more polar as compared to the excited state. So the ground state is stabilized more than the excited state. And this is evidenced by an example. Absorption maximum of acetone is at 279 nanometer in hexane as compared to 264 nanometer in water. Water being the more polar solvent, you can see there is it shows a absorption maximum or lambda max at 264. But in hexane, which is more non-polar, so it will show at a longer wavelength. So by increasing the polarity as seen in water, we will see lambda max shifting to shorter wavelength. Now looking at the pi star transition, you see almost the opposite effect. So the absorption band moves to longer wavelength. That is, it undergoes a bathochromic shift or a red shift by increasing the polarity of solvent. So when the solvent polarity increases, then you will see a bathochromic shift for the pi star transition band. This is because the excited state is more polar as compared to ground state. So in a polar solvent, the excited state is stabilized more than the ground state. The dipole-dipole interactions with the solvent molecules lower the energy of the excited state more than that of the ground state. I mentioned it is more stabilized. What exactly stabilization means is the dipole-dipole interactions with the solvent, which is more polar, lowers the energy of the excited state, which is more polar, more than that of the ground state. You can see in this diagram this. Here you have on the right side the more polar solvent, and this is the less polar solvent. Now here you see the N pi star transition, and here you see the pi. So this is the less polar solvent. What is the effect of increasing the polarity of the solvent? We'll see on the right side. So this represents N pi star transition. This represents pi star transition. As we saw in the pi star transition, the excited state is more polar, it is stabilized more, and it is lowered more because of more dipole-dipole interactions. So you see the energy of this pi star in presence of a more polar solvent coming down. So what happens to the gap between these? Whereas the ground state is not lowered that much in energy. There is a lowering in the more polar solvent, but you see a very slight decrease, whereas here there is a greater decrease. Ultimate effect is the difference in energy between these two states, pi and pi star, in a highly polar solvent reduces. You can see this length is reduced compared to this length. If you see, this is the energy axis, so that means lesser energy is required for undergoing pi-pi star transition in a highly polar solvent. And since lesser energy is required, longer wavelength would be absorbed. That's why we get a bathochromic or redshift in whenever polarity of solvent is increased. This is true for pi star transition. We also saw about the n-pi star transition. In the n-pi star transition, the ground state is more polar than the excited state. So here what happens is, this is stabilized to a greater extent. That means the energy of the ground state in a highly polar solvent is lowered to a greater extent than the excited state. Effectively, what happens is, the difference in energy between ground and excited state in a highly polar solvent would be more. As evidenced by this arrow and the length of the arrow, this is increased, this is reduced. So when the polarity of the solvent is increased, the n-pi star band will show a shift to shorter wavelengths. Because energy required is more, wavelength would be shorter. That's why we see a hypsochromic shift for the n-pi star transition on increasing the polarity of the solvent. N orbitals are stabilized more than the pi star orbital in the n-pi star transitions. I hope this is clear now. So now we go into the theory of spectrophotometry. We have finished with most of the general topics. Now this will be more concerned with UV visible, so we will be going into it, but we're still in the absorption spectroscopy. Most of them apply, but I will be mainly explaining based with respect to UV visible radiation. So when light falls on a homogeneous medium, a portion of light is reflected, a portion is absorbed, and the remainder is transmitted. Okay, so when light falls on a homogeneous medium, a part of the light is reflected, a part may be absorbed, and the remainder is transmitted. So here we have the equation IO equals IA plus IR plus IT. What is IO? IO is the intensity of incident radiation. IA is the intensity of absorbed radiation. IR is the intensity of reflected radiation. And IT is the intensity of transmitted radiation. So we can see that now IR is reflected radiation, and this we can keep it to a minimum by ensuring that reflections do not take place. That means the cuvette or the cell in which you take the sample, that must be completely transparent. You should not have anything which will cause reflections, like any dust particles, any cracks, any scratches, all these, or fingerprints on the cell will result in reflections. So if we keep reflections to a minimum, or even when you use two identical cells, one for the solvent and one for the sample, we cancel out the effects of reflection. In that case, we would say IO equals IA plus IT. So what is not absorbed would be transmitted. That is the general thing that we usually consider. Now we go into the laws of absorption. Very important for you from your exam point of view, and also especially for quantitative analysis. We have two laws of absorption in describing the phenomenon of absorption. Two laws we have, and both are complementary to each other, and both are considered together in order to understand the phenomenon of absorption. The first law which we would consider is the Lambert's law. So what is Lambert's law? How is it? What does it state? This has to be stated exactly the way the law is. You cannot use your own words here. So the law states When monochromatic light passes through a transparent medium, the rate of decrease in intensity with the thickness of the medium is directly proportional to the intensity of light. So when monochromatic light passes through a transparent medium, the rate of decrease in intensity with the thickness of the medium is directly proportional to the intensity of light. This is the way Lambert's law must be stated. But there is also one more way, which is a very simple way. So in case you are not able to remember the law in that form, at least you should be able to write this. But the first one is always the preferable way because your derivation of the equation for the law will start from that definition. So you can also state Lambert's law as intensity of transmitted light decreases exponentially as the thickness of the absorbing medium increases arithmetically. This is not what exactly the Lambert's law states, but it is what it implies. So intensity of transmitted light will start decreasing in an exponential way as you go on increasing the thickness of the absorbing medium. So as the thickness of absorbing medium will become more, the intensity of transmitted light basically decreases. It's an exponential relationship or a logarithmic relationship. So coming back to the first definition, we will now see the derivation. What did it state? When monochromatic light passes through a transparent medium, that means it should be a homogeneous medium. There should be no suspended particles. Okay. The rate of decrease in intensity with thickness. So here you see the rate of, why the negative sign? Because the rate of decrease in intensity with thickness. That means as thickness increases, the rate of decrease of intensity. So it's an opposite effect, and therefore we put a negative sign. So derivative of I by derivative of B, di by dB. So because one increases with as thickness increases, the decrease in intensity, as the law states, is directly proportional to the intensity of light. It refers to again the incident light. So here you have I is proportional to I. So minus di by dB is proportional to I. That is how we first come to this equation, directly from what the law states. Now we'll try to remove this proportionality sign. You have minus di by dB equals ki. So what is k? It's a proportionality constant that you have introduced. So you get rid of this proportionality, proportional sign. You get minus di by dB equals ki. What is I? It's the intensity of incident light of wavelength lambda. What is B? It's the thickness of the medium in centimeters. And K, of course, is the proportionality constant. Now, since we had derivatives, we'll be integrating that equation between the limits I equals IO when B is equal to 0. Okay? What it means is, if thickness is not there, there is no solution, then intensity of light measured would be the intensity of incident light. IO is the intensity of incident light. This is the lower limit, and the upper limit would be I equals IT when B equals B. So at any thickness B, what is I? I would be equal to the transmitted light, because the moment you have some thickness, there will be some absorption, because the solution is capable of absorbing that wavelength of light. And if there is absorption, there will be a decrease in intensity compared to incident light. And this decreased intensity is what is intensity of transmitted light. So we say I equals IT when B equals B. So this is the lower limit and this is the upper limit. So when you integrate, you will get logarithm. This is natural logarithm. This is L, Ln. Okay, natural logarithm IO equals KB. IO by IT equals KB. So this is IO by IT equals KB. So this IT in the denominator, if you take it on the other side, you will take it as ln of IT equals ln of IO minus KB. KB you take it on the left side. So what you can do is IT is taken on this side, KB on this side. So it will be KB ln of IT minus ln of IT equals ln of IO minus KB. You remember the ln signs, then you can raise KB as a power e raised to minus KB. So you will ultimately get IT equals, because ln of IT equals ln of IO minus KB. Therefore, IT equals IO into e raised to minus KB, where IO is the intensity of incident light falling upon an absorbing medium of thickness d centimeter. IT is intensity of transmitted light after passing through an absorbing medium of thickness b centimeter. And K is a constant for the wavelength and the absorbing medium used. Now we change from the natural to common logarithm, that is log to the base e to log to the base 10. So that we can do by dividing by 2.303. 1 by 2.303 is nothing but 0.4343. So you can get to this equation, IT equals IO into 10 raised to minus 0.4343 kb. It can also be written as IT equals IO into 10 raised to minus kb divided by 2.303. 1 by 2.303 is 0.4343. Okay. Now this we are going to reduce it to capital K. So IT equals IO into 10 raised to minus capital K small b, where capital K is small k by 2.303, or it is 0.4343 small k. Okay. It is called the absorption coefficient. Absorption coefficient is defined as the reciprocal of the thickness required to reduce light to 1/10 of its intensity. It is the reciprocal of the thickness. That means 1 by B. It is the reciprocal of the thickness required to reduce light to 1/10 of its intensity. So if you have 1 by B thickness, then light will be 1/10 the intensity. So IT by IO should become 1/10. IT by IO should be 1/10. That is zero point 0.1. And we can, from this equation, if you take IO down, IT by IO will be 10 raised to minus capital KB. And IT by IO is 1/10, so it is equal to 0.1. It is also equal to 10 raised to minus KB. So here you rearrange, you can remove this 0.1, that is 10 raised to minus 1 equals 10 raised to minus KB. So both the powers would be equal. So minus KB equals minus 1. Therefore, KB equals 1 and K equals 1 by B. That's how we come back to this definition of absorption coefficient. It is defined as the reciprocal of the thickness required to reduce light to 1/10 of its intensity. So this was Beer's law equation. IT equals IO into 10 raised to minus capital KB. Equation 2 is the Lambert's law equation. The second law of absorption is Beer's law. So what does it state? It's similar way, both the laws state the same words except one change. So instead of the thickness here, you will actually have, you will be having concentration. So actually it will be concentration for the Beer's law. So you will have to remember the definitions exactly. So the Beer's law, what it states is, when monochromatic light passes through a transparent medium, the rate of decrease in intensity with the concentration of the medium is directly proportional to the intensity of light. Okay, so it's the same except in Lambert's law it was thickness here. So when monochromatic light passes through a transparent medium, the rate of decrease in intensity with the concentration of the medium is directly proportional to intensity of light. As the concentration increases, the rate of decrease will be proportional to the intensity of light. Or you could have also what it implies is the intensity of a beam of monochromatic light decreases exponentially as the concentration of the absorbing substance increases arithmetically. So it's a inverse logarithmic relationship between the intensity of light and the concentration of the solution. So using the first one, we'll again derive the same way as we did for Lambert's law. And ultimately, we'll get IT equals IO into e raised to minus small k dash c, where small k dash is the proportionality constant. In place of k, what we used, we are now using a different proportionality constant, k dash. So you will have to start the derivation right from minus di by dc is proportional to I, and then follow it with removing the proportionality sign, minus di by dc is equal to k dash I. Then integrating between the limits of I equals IO when C is equal to 0 to I equals IT when C equals C. So wherever you have B, you need to now use the concentration term C. And when you integrate, ultimately you get IT equals IO into e raised to minus k dash C. Then converting to a natural logarithm to common logarithm, you get IT equals IO into 10 raised to minus 0.4343 k dash C, or 10 raised to minus k dash C by 2.303. And then for using capital K dash for small k dash by 2.303, we will get the final equation for Beer's law, IT equals IO into 10 raised to minus k dash C. So this is the final derivation of Beer's law equation, and this is Beer's law equation. So if you compare where C is the concentration in grams per liter, K and K dash are constants. So K we used in Lambert's law, K dash we have used in Beer's law. B we have used in Lambert's law. B is the path length in centimeters. C we have used in Beer's law, which is the concentration in grams per liter. So combining equations 2 and 3, 2 for Lambert's law and 3 for Beer's law, we get IT equals IO into 10 raised to minus ABC. B from Lambert's law, C from Beer's law, and A is a new constant that is introduced instead of K and K dash. A is called the absorptivity. A is called the absorptivity. So now rearranging this. So what you do is take 10 on raised to minus ABC on the other side. So it becomes 1 by 10 raised to minus ABC. That becomes 10 raised to ABC. And IT you take on this side. So it becomes IO by IT equals 10 raised to ABC. So you take the logarithm of this. On both the sides, you get log IO by IT equals ABC, because when you take the log of this, you will get ABC. And what is log IO by IT? We have seen last class, it is nothing but absorbance. So absorbance A equals ABC. This is a form in which you can remember it very easily. That's why I've adopted this. This is Beer-Lambert's law. There are alternate terms used instead of for absorptivity. Instead of A, some places you will also see small k, and instead of B, you may see T. So KCT would also be given as Beer-Lambert's law. It's easier to remember in this form, and that's why I have used these. These are the more commonly used terms. Small a for absorptivity and B for path length. So capital A equals small ABC is Beer-Lambert's law, very important law, and it can be further written in one more form, the more commonly used form, because if you change the concentration C and express it in moles per liter, then A equals epsilon BC. Epsilon also we have seen earlier, it's molar absorptivity. So epsilon is molar absorptivity, and we will get Beer-Lambert's law as A equals epsilon BC. So if it's a very common question asked in your exams, state Beer-Lambert's law and derive an equation for the same, derive a mathematical expression for the same. So this whole derivation is important. You'll have to indicate all the steps one by one, starting with always the first one, the derivative equation minus di by dv equals is proportional to I, or minus di by dc is proportional to I in case of Beer's law. Derive both of them, get Lambert's law separate, Beer's law separate equation, combine the two, and finally get A equals ABC, and also mention the more common, popularly used form A equals epsilon BC. So this actually completes the Beer-Lambert's law, very important topic in your chapter of absorption spectroscopy. Application of Beer's law to mixtures. Now, so far what we saw, A equals ABC, that or A equals epsilon BC, that is when you have a single substance in your solution. You measure the absorbance and you can find the concentration, because absorptivity A, small a, or epsilon, molar absorptivity, both are characteristic of a substance. So A equals epsilon BC, in that epsilon is characteristic of the substance, B is the path length, which is characteristic of the cell or the instrumental component that we're using for measurement. It's not going to change. So in other words, we always say absorbance is proportional to concentration. So if absorbance is proportional to concentration, if we measure the absorbance, we can find out or calculate the concentration of an unknown solution. So that's application of Beer's law to a single component sample. But if the sample has number of components, that is, we are considering the sample to be a mixture, then how would you apply Beer's law? Then we would say the absorbance that is measured would be the total absorbance of all the absorbances of all components. Or in other words, A total equals A1 plus A2 plus A3, and so on. Depends upon how many substances are there in the mixture. So each of them will have their own absorbance, and the sum of all those absorbances gives you the total absorbance of the solution. This is of course true, and you can use this equation provided there is no interaction between the individual components. If there is no interaction, then this equation holds true. So further, we can see that A1 would be epsilon 1 BC1, A2 is epsilon 2 BC2, A3 is epsilon 3 BC3, and so on. The subscripts refer to absorbing components 1, 2, 3. So this is 1. This is component 1. Absorbance of component 1 would be epsilon 1 BC1. Why we have not put B1? Because B remains the same as you're making the measurement in the same instrument with the same cuvette or sample cell. So the B will remain same. The path length will be the same. Epsilon, why we have put subscript 1? Because as the substance changes, the epsilon value will change. Different substances will have different epsilon values. And that's why epsilon 1, I told you epsilon is characteristic of the substance. So for this substance, it has its own epsilon value. C1, we are trying to find the concentration of the component. So C1 has to be an unknown quantity. C1 can be equal to C2 or it may be different. If both components are present in the same amount in the mixture, it can be equal also. Or it could be different. But these are what we need to find out. These are the unknown quantities. So this type of equation can be used for mixtures where the individual components do not interact with one